Hello? Have you seen my reply yet? Never mind. Let me know if you have any problem. Testing 1, 2. Okay, very good morning to everyone. Hope you guys are ready for the lectures today. Let's get straight to the story because today we're going to have 30 minutes quiz. We will probably do it in the last hour. Okay, so we'll have lecture first. Okay, so some of you say that maybe the concept of 1-2 and 1-to-1 is not quite obvious. Okay, so these actually coming from geometry. So I'll talk a bit about geometry, and then today I'll try to avoid doing row reduction in class. Okay, because I believe you can do row reduction already. So I'll leave it to you so that we spend more time talking about concept. Okay, so there are two examples you can keep in mind, two linear transformation you can keep in mind. So first one I'm going to tell you is something that's not onto, and then second is onto. So not onto example from, okay, from a 2D space to a 3D space. Okay, imagine you want to put a plane, okay, a piece of paper inside a box. Can you fill the box with a paper? Yes or no? No, right? Okay. So imagine you have the linear transformation, okay, T1 from a 2D space. You can imagine as an infinite extended plane, okay, and you want to put it inside R3, okay. So there's an extra coordinate here. And I draw the box. So you can never be onto from a small dimensional space to a larger dimensional space. So you can only fill out a piece of it. You cannot be onto. Okay? But if you go the other way around, from R3 to R2, okay? You can imagine you got a box or a tin, okay? If you drinks any soft drinks. So you smash it down, okay? Smash it to flat. So you map it into R2, okay? So in this case, you can be onto. So if I swap further arrow, if we swap the row of the map, first one is this, we call this inclusion. And then second, if we call it, how about we call it smash? And we smash the box into flat. Into 2D. Okay, this is something onto. Okay, so you might wonder, since you say that every linear transformation can write into matrix form, so what's the matrix for these two map here? Okay, so what should be the size of the first linear transformation? What's the size here? 3 by 2, good. Okay, so it should be a 3 by 2 map here. So what should be the entry? 3 by 2. Okay, so in this case, I just map the first entry to the first 3 by 2. Okay, yeah, right. And then I've map it to first x, I map to x. Okay. E1, I map to E1. Let me put it here. E1 map to E1, okay, and then E2 map to E2. So I should put this as E1, E1, E2. Okay, here we have E1, E1, E2, and E3. Okay, so it's a 1, 1 on the 2D side, and then 0 on the Z component. Okay, this will do the inclusion. How about T2? What's the size of T2? 2 by 3. Good. So what do I do? Similarly, I send E1, E2 to the same place, and then I forget the Z component. So let me call this the proper thing is forgetting E3 component. I forget the height. Okay. So sometimes you will see that, you will hear that. Okay. I also talk to some of you. You'll hear that ants, ants and insect. Ants. Does everyone know ants? Ants. 蚂蚁, yes. Okay. 蚂蚁. Ants. So ants, you will hear people say that ants is a 2D creatures. Okay. Because it is so small, when you crawl on a piece of paper, you don't know where you are. Yeah. You only can see locally what happened. For example, you, okay, you, human. So you walk until Antarctica, okay? Do you realize that it is lower than Malaysia if you just walk? Right, okay? So in 3D, if we put 2D space in 3D, we can put it differently. Okay. So I think in the textbook you have a map that writes something like let me put something like this. T3. Let me introduce T3. So T3 is like 1, 0, 0, 1. Okay. You still have the plane here, but I change the Z coordinate. How do I change? I change according to the coefficient X and Y. Okay. So I add up X and Y component here. Okay. So when I add up, so when the point is further away from the square, and then the height will increase on one end and decrease on the other end. Happen differently on the other corner because plus and minus. But what I want to tell you is when we map between dimension, we have freedom to change the geometry of the space. Okay. Okay. Anyway, next. So let's see whether these two are one-to-one or not. Okay. So for example, the first one is this T1. Is T1 one-to-one? I think one of you, Sanqing, put out some notes on the student forum. I encourage you to go and see, maybe make some reply if you agree, okay, or you disagree. So, okay, let's come back. How about T1? Is T1 one-to-one? Is T1 one-to-one or not? How to check something is one-to-one? Ax equal to 0, where if and only if x is the only trivial solution, right? So if you solve this T1 using homogeneous system, what solution do you get? So there'll be a quiz today, okay? So what's the solution if you solve this as a homogeneous system? What do you get? What solution you get? Anyone? Hmm? Anyone? What solution do you get from this augmented matrix? Hmm? What do you get? Yeah, x equals 0. So x1 equals 0, x2 equals 0. If you have issue, you should ask. This is before quiz, you should ask. Okay, so in this case, T1 is 1 to 1. So from diagram, how do you see 1 to 1 here? Okay, you can see that every point just get mapped to one point in the codomain. Okay, one picture. How about the next part? Is this T2? Is this 1 to 1 or not? No. Why? Why? Not 1 to 1. Why? S3 is free. Good. So if you solve this matrix in a homogeneous system, you found that S1 equals 0, S2 equals 0, but S3 can be anything. Okay, so it's not 1 to 1. So from picture, what do you mean by S3 can be everything? You can see that the top point got sent to the plane, and the corresponding bottom point also gets sent to the point. Okay, everything along this line gets sent to one point. Okay, so this is not 1 to 1 because the more than one point gets sent to the same point. Okay, so this is what's going on in the geometry. So every matrix you can realize as linear transformation, and then you can realize as a you can see it in the geometry. Okay, good. Any question about this? Any question? Let you think a bit before we go into the content today. Okay, try keep this example in your mind so that you know what's going on. Okay, all right, no question. Okay, so let's resume from yesterday. So yesterday we say that if we start with a basis, okay, immediately in your mind you can form some basis in your mind. For example, in R2, maybe make it darker. So in R2, okay, have some basis in your mind. For example, the standard basis 0, 1, and 1, 0. So every element in R2, okay, can be uniquely written as a linear combination of the bases. So for example, if we take x equal to 2, 1, then you can write it as 2 times the second basis vector plus 1 time the first basis vector. And then the coordinate for this linear combination, we call it a coordinate vector of x relative to the basis. We will collect it as a column vector. Okay, so it's like a name for the vector. Okay, so if it is a name, it should be unique, right? So why is it unique? Is it unique? So why is it unique? And so the claim here fix a basis. The coordinate vector is unique. Okay, so proof. So coordinate vector is unique. Suppose it is not. Okay. Suppose it is not. Then you can write x equals to maybe C1 V1 up to Cn Vn. Okay. Is it using n? P. Okay, use P. P. Okay. For some scalar Ci. Okay. And possibly you can write it in another way. Maybe D1 V1 plus until Cp Vp. Okay. For some other scalar Di's. Okay. Let's say they are different. Okay. Suppose they are different. Okay. Then consider x minus x. So what's x minus x? You get first expression, take away the second expression. Okay. Okay. Take away the second expression. Okay. So on the left hand side, what do you get? X minus x. What do you get? 0. Good. On the right hand side, what can you do? You can collect the like term. Okay, collect the coefficient C1 minus D1 V1 plus dot 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 plus until Cp minus dP Vp. Okay, so what's this vector equation here? 0 equal to some linear combination. What's this? This is the equation that you consider in the linear independence, right? But what are Vi? What are V1 up to Vp? They are the basis of the subspace. Okay, they are the basis. So basis satisfy what condition? Two conditions: span and linearly independent. Okay, so definition of linearly independent. You have this equation here. If and only if the coefficient, the solution are all 0. Right. So if and only if Ci minus Di equals 0 for y. Okay. So in this case, this implies what? This implies C1 equals to. Okay. So at first you might think, how is it useful for that linear independence condition there? Okay, this is one place you can use it. You can show that the coefficient is unique. Okay. So this is the one place you can use it. Okay, next. This example, I will explain it, then I will skip this. Okay. So this example here is you are given V1 and V2. Okay. Two vectors in R3. Okay. And then you're given X. So you ask X is in the span of V1 or V2 or not. So meaning if X is X, a linear transformation, linear combination of V1 and V2 or not. Okay. So you will go and solve the augmented matrix again. So the solution you get is exactly the coordinate vector. Okay, because coordinate vector is the coefficient that you use to express the vector in this in terms of the v1, v2 here. Okay, so okay, I will leave you to solve this augmented matrix. I will do it as well, and then you will check answer later. And what is this doing? Okay, it's shown in this picture here. So this vector lives in an R3 space. Okay, so you got an R3 space here, and you have two linearly independent vectors. We haven't checked. You can check it. So if they are linearly independent, they form something like 90 degree. Okay, so they form a plane. Okay, so if you want to ask whether x is in the span or not, that means you are lying. X will be lying in the plane of plane that's spanned by v1 and v2. Okay, if it lies on the plane, then it is a linear combination of v1 and v2. If it lies outside the plane, then it is not in the span of v1 and v2. Okay, so this is the geometry meaning of span. Okay. Okay, next. Okay, next is the dimension. So we got a basis, so we can count how many vector inside the basis, and this is the dimension. Okay, so the dimension of a zero subspace H, okay, we write dim H, is the number of vectors in any basis. Okay, so we count how many vector in the basis. And the dimension of the zero subspace is 0. Okay, so this quite match our geometric intuition, right? Yesterday, someone asked me, is 0 vector a point? Okay, I said yes, so it's a point. So this dimension should capture this information here. So the dimension of zero subspace is 0, no dimension. Okay, so if you have a vector, okay, so for example, if you have a vector, okay, just look at here. So 0 here. If you have a vector 1, okay, in R. So if you look at the linear combination of them, okay, so you can look at the linear combination of them. So you can look at 2, 0.5 on 0.5 is here, sorry. And then maybe -1. So all the way. So you get a line. Okay. So if there's one vector in your basis, then you will form a line. 2 vector, you form a plane. 3 vector, you form a box, infinitely extended box, or R3. Okay, so this matches what we want to capture the dimension of the space. Okay. Any question up to here? No? No? Okay. So far, so good. Okay, next, rank. What's the rank? Rank is the dimension of the column space. Okay. When we count the dimension of the column space, we call it a rank. Okay. Let's say we want to determine the rank of this matrix. Okay. What we did yesterday is we raw reduce it. Okay. After we raw reduce it, let's say we already raw reduce it. Okay. I leave you to check this. Okay. Let's say we already raw reduce it, and then we want to find the pivot column. Okay. So where is the pivot column? You need to tell me where's the pivot column. Where's the pivot column here? If I have this echelon form. Where's the pivot? Okay, how many pivot do I have? 3. Okay, what's the first one? 2, -3, and then 4. Good. Okay, so your pivot column is the first one, second one, and the third one. Okay, so from yesterday, what's the basis of column A? What's the basis of column A? What's the basis of column A? Yesterday. content. Should you pick the first, second, and sorry, this is the fourth one. Fourth column from the original matrix or the reduced one? Original or the reduced one? Which one do you pick to be your basis of code A? Do you pick A or the reduced A? A, okay? So you need to pick from A. So the basis for code A is basis for code A is, let me see, what's the definition of basis again? It is 2460,579 minus 9, and then it's formula's root. Okay? Because you can realize that there's all 0 in the last row here. Okay? If you pick vectors from the reduced A, you can never generate non-zero number in the fourth row. Okay. So you always remember that code A is never the same as a code reduced A. They are never the same. Okay. You have to always pick from the original matrix. Right. Okay. Based on the pivot you have. Okay. So in this case here, the basis for code A is these 3 vectors here. So what's the rank of A? What's the dimension of code A? What's the rank of A? What's the dimension of code A? How many vectors there? 3. Okay, good. So the rank of A is 3. That's all. Okay, we just count the number. There's nothing special here. So the rank of A is 3. Okay, because there are 3 vectors here inside the basis. Okay, so pivot column of matrix A form a basis for the corner space of A. Okay, so far still okay? Okay, how about this part here? The rank theorem. Okay, so if A is a m times n matrix, okay, when rank A plus dimension of the null space of A is equal to n, okay, and the rank A is equal to rank A transpose. Okay, let's look at it one by one here. Maybe we keep this. We keep this. Okay, this is not reduced yet. So let's borrow some example from yesterday. Yesterday we did one, I think, quite useful, and then we have shown quite a few things. Let's borrow some from yesterday. Let's borrow this one. This one. Yeah, this one. See if I can cut this guy. Okay. Okay, let's see this theorem in some examples, and then the example will generalize to general cases. Okay. What should I keep here? Let me remove everything. Okay, so let's look at the first one first, and then we'll look at the second one. So rank A plus dimension of now A equal to n. Okay. So let's verify this. Before you read the theorem, you should convince yourself this theorem is true first. Okay. So let's convince ourselves why rank A plus now dimension of now A is n. So when you get a matrix, how do you find the basis? What's the first thing you do? Huh? Find the pivot. Who said the answer? Okay, yeah. Find the pivot. So this means you want to raw reduce your matrix first. So in this case, we only need to care about raw reduced matrix. Okay. So let's have some raw reduced matrix on your hand. Okay, let's take this A here. So you want to find pivot. Okay. So in this case, which columns are the pivot? Which column? First one, second one, and the fifth one. Okay. So you have five. Sorry, have three. So you have three pivot columns. Okay. So your rank is equal to 3. Okay. And A is what size of A? What's the size of A? What is the size of matrix A? 4 by 5. Good. Okay. So just now we have that rank A plus dimension of now A is equal to n. Okay, which is 5 in this case. Okay. M times n. And the rank is 3. So 3 plus dimension of null space of A equals to 5. So in this case, this dimension of null space should be 2, right? Okay. So where do you find the 2 dimension from in this example here? Do you have any idea where to find the 2 dimension from? Any idea? Where to find the other 2 from? Any idea from there? No. Any idea? Any idea? Huh? Column without pivot. Okay. In other words, what's the variable which is not a pivot? What do you call it? What's the variable that is not pivot? Free. Yes. So you look for the free variable here. So what's free here? So here is S3 is free and S4 is free. Okay. So you might wonder, I still don't believe yet. Can you produce the 2 vector for me? The basis. Remember, when we solve for null space, what's null space? X is in the null space of A if AX equal to 0. That means you need to solve the homogeneous system. Okay. So when you solve the augmented matrix with the homogeneous system, can you get out the parametric vector form for me? Let me copy down first. So what is the parametric vector form? X1 minus 3 times x3 plus 5x4 equals 0, and then x2 plus 2s3 minus x4 equals 0, and then x5 equals to 0. So what's the parametric vector form? So x equal to x1, x2, x3, x4, x5, and then x1 will be equal to 3x3 minus 5x4, and then x2 equal to minus 3x3 minus x4, And then S3 is 3, S4 is 3, S5 is 0. Okay? So can you split this into two vectors here? What's the first vector you get? Respond to S3. What's the first vector you get? Huh? What's the first vector? 3, 2, 1, 0, 0. How about second one? -5, -1, 0, 1, 0. So you read out the coefficient here. Okay. So this is the two vector that span the basis that span the space of now A. So let me write somewhere. Let me write here. So basis of co-A first. Basis of co-A is 1, 0, 0, 0, 0, 1, 0, 0. The pivot column 0, 0, 1, 0. And then basis of now A is 3 minus 2, 1, 0, 0. And then -5, -1, 0, 1, 0. Okay. So 3 plus 2 is equal to the n, equal to the number of columns. So you will see that basis of now A always attached with free variable. Okay? This is your observation. It will always attach to a free variable. Okay, and then yesterday we already shown that this thing here will form a linearly independent set, and then they span. They span precisely because of this equation here. Any solution that write in the linear transform, linear combination of these two vectors is the solution to AX to 0. Okay? Any question? Any question? Okay, still following? Still following? Okay. Any question? No? Okay. So 3 plus 2 is 5. Okay, so we found all these things. So every column is very useful. So either you are a basis for column A or you are a basis for now A. But basis of now A not automatically obtained from the matrix. You need to find the parametric vector form. Okay. And also you see that, sorry. Okay, something to observe here. You can see that this now A actually is different from core A, the space they live. Core A live in R4, and then now A live in R5. Right? Okay. So you can never get now A from the column of A. You see it? They live in different space. One got 5 entries, one only have 4 entries. Okay. So now A live in R5, and then core A live in R4. One is horizontal, one is vertical. They live in different spaces. Okay, something to note here. Okay. Second is rank A is equal to rank of the transpose A. Rank of A equals to rank transpose A. See, is it easy to see? Okay, maybe it's kind of easy to see. Let's use this example again. So duplicate. Okay, so similarly, if you want to find rank, you need to row reduce your matrix. So you can start with a row reduced matrix here. So if you transpose this A, what do you get? You get 1, 0, -3, 5, 0, and then 0, 1, 2, -1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay. So what's the pivot column for AT? Can you find the pivot column? Can you find pivot column for AT? Can you find it? What is it? Which one is the pivot for AT? Huh? Huh? What? Third? Okay. Then just third. Yeah, just third for now. Okay, because this is not even a echelon form yet. Okay, but you can see that if you pick the first one and the second one, first one and the second one, okay, and you can make everything below 0 as well, right? Okay, so in fact, if it is a pivot column before transpose, is the same as the pivot column after transpose. Okay, they still say the same. So you can see that you can get rid of this non-zero term below the 1. Okay, and then above 1, it is already 0 because this is done in A. When you reduce A, this guy automatically becomes 0 already. Okay, so a transpose will preserve the number of pivot columns. And also the size. Size, yeah, size. And not size, I mean the position of pivot column. And so the claim is transpose preserve the position of pivot columns. Okay, so how many pivot you have before is the same as how many pivot you have after transpose. So their rank is the same. Okay. Okay. Any question? No. Okay, next. Okay, let's say we have examples here. Let's think how to use this theorem here. So part A, if A is an 7 by 9 matrix, okay, so you can imagine 7 by 9. With a 2-dimensional null space, what's the rank of A? What's the rank of A? What's the rank of A? Using the theorem. Hear some sound, but I cannot hear clearly. Rank A plus dimension now A equals to n. So what is n in this case? 9. What is dimension of now A given in the question? 2. So you want to find rank A. So rank A is? What? Louder, please. Rank A is 7. Okay. Okay. So you could imagine that there are 2 free variables after row reducing A, and then 7 pivot column. Okay. E. Could a 6 times 9 a 6 times 9 matrix have a 2-dimensional null space? Yes or no? 6 times 9. 1, 2, 3. See, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. So 6 times 9. Can you have a 2-dimensional null space or not? Why? You can only have 6 pivot. You can only have 6 pivot. Yes, correct. So rank A at most 6. Okay. Your rank A is at most 6, and then you have 9 columns. So 9 minus 6 is 3. Is 3 is wait, let me and 9. Okay. So your rank A is at most 6. So your dimension of now A is at least 3. Okay. So you cannot achieve two-dimensional null space. So your dimension of A is must at least 3. So if you can do something like this, so let me draw it up. So at most, the best you can do is 6 pivot. Okay. So you must have 3 free variables. Okay, depend on where it is, but you must have these 3. Okay, so far okay. Okay, there's nothing special here. Just play around with numbers, and then restriction of size. Okay, next is the basis theorem. Okay, so what's the basis theorem? So if H is a p-dimensional subspace of Rn, okay, so it's the base p-dimensional, meaning you have p vectors in your basis. Okay. So this theorem is telling you how to find the basis. And how to find the basis. One way is any linearly independent set of exactly p elements in H is a basis of H. So it says that if you have exactly p linearly independent vectors in your set, then it will automatically span. Okay, so it form a basis. Or the other way, any set of p elements of H that spans H is a basis of H. That means you have any set of p elements that span of H, it automatically linearly independent. Okay. So this is kind of a strong result here. I was thinking I want to explain or not. Okay, maybe let's start from the second one. Okay, before we end this hour of lecture, let us spend some time with this basis here. Okay, let me squeeze this thing down. Okay, maybe let's start with number 2. Start with number 2. Okay. Before this, we should have a spanning set here. Spanning set here. So the idea is what? The idea is let me see how to. Or maybe if you do you have any question first? Do you have any idea? Do you have any question? Not sure if I want to explain this part. If we don't prove, then not very useful. But the proof is a bit twist, a bit play around with logic. So not sure if I want to prove it as well. Do you have any idea on this two theorem statement here? So first one is I can start with linearly independent set and then I find the basis. Second is I start with a spanning set, I find the basis. Let me think. Okay, let me think of a way, see if I can find better way to present this theorem. Then next time I will bring this theorem back again. Okay, next time I'll bring this theorem back again. See if I can find a better way to say it. And I post some YouTube link on Moodle. If you notice, it's by the 3 blue 1 brown. Okay, because they animated the concept of linear algebra. So if you wonder how they made animation on the geometry of linear algebra, you can go and watch it. Okay. 3 blue 1 brown. Okay, for this basis theorem, let me find a better way to present to you. Next time I'll bring it back again. Because yeah. Okay. If you have any idea or input, you can tell me. But practically, this is not okay. Practically, it's useful, but maybe not very useful for this the setting of this course here. Yeah. Okay. Anyway, let's take a break until 9 o'clock, and then we will continue new chapter. OK，因为你有，OK，这个是普通的 rotation 的 matrix，OK，这是你放什么 theta 它就怎么转了。如果它是要这么转，你就放相对的 theta 进去哦。然后你可以看到，你看这两行的关系，如果你懂了一行，你就知道另外一个。因为如果你懂这两个数字倒转啊，你再放一个减，它就是这一列的数字。OK，好，然后这个的问题是说你要 rotate 加上 reflect，OK，所以你先做这一个，然后你再做多一个 reflection through horizontal x1。所以 reflect 的 matrix 你知道是长怎样？你知道长怎样吗？OK， 顺时针转，然后第二个是 reflects points through the horizontal x1 axis，所以是说它上面变成下面，下面变上面，所以它的它的 S 和 Y 倒转
，Y 变成向外
啊
，X 变 Y
，Y 变 Z， 哎 Y 变减，对，所以是1跟减这样子啊，对不对？所以它作用在这个的上面是这个是一样的，然后这个就变成减和减，对吗？没有，这个是3次，对吗？所以你这一个变减嘛，对不对？所以你现在知道这一边这个是减，所以你知道这一个是减1/2哈，减 square root 1/2，然后这个是 square root 1嘛，对不对？所以你看 cos theta 等于这个，减 cos theta 是不是等于这个？然后这个是减 sin theta 等于这个，那减 sin theta 是还是等于这个？所以你就得到这个 matrix。
是一旦出现这种2乘2，
对，
就已经是个2乘2。
对，
这个理解是不是能够看成计向量？是，
这样子，
就是 机向量就是这个是机向量，然后转
哦
换以后
，OK，
这个是
standard
机向量
basis。对，机向量的 image，
那个
standard basis，对吧
这个
？hint 就是他给你的那个hint
因此
hint
提示
提示，
哦
对对对，提示，不然情况。
是
OK OK，
这个为什么一定是左乘？就是这种东西一定是左乘，
我们定
然后那右乘会怎么样？
可以右乘，但是你可以不同的定义。
那就是左乘，然后这个能直接用吗？那这是去年的 quiz，
去年你也拿得到，这样厉害，
不是别人发给我，
这么惨，
写了一个这个，
我都不知道那个 theorem 是什么。
就是说正 one to one 的那个。
OK，不重要，
今天
重要的是这个，这个是说这个如果这个是对的，这个就是 one to one，这个定理就可以丢掉，然后记住这个结果。
那这个能
结果
直接用吗？
这结果可以用，这个结果就刚才我也在用，
直接用啊。
刚刚我也在用，我一开始我也在用。
还有
theorem 肯定是可以用的，谁发的你这样厉害？
高数班的 Q，
哇，等下如果真的是这里出的不是惨，
这个这个 so 的是
他是说把 A 设置成这3个 column
这
vector
它
线，
题目只要点，然后它上面的算出来，下面又跟这样，它这是在干嘛？
嗯，我其实不知道为什么要做多余的东西，我不，
其实是不用的。
他应该要写在它的前面，他应该要写在前面，就是这个写在这个前面，
应该
A B 等于这个，
这个是通用符号，是不是不是？这个，它这个 ij 是不是通用？
我叫通用。
是只在题用。
AJ 只是说那个 IJ 的那个点是什么？就
所以这是通用，
什么叫通用？
就是其他地方举证也
可以啊，可以啊，可以啊，它只是在指说这一个 matrix 里面的 IJ 那个位置那个数，比如说这个的意义就是这个 x 一，不对，应该是相乘哦，所以是 x 一乘 y 一。对，
这样对。
是吧？
那个什么不是，不止刚才讲，就是经常不是现在算出来会，
哪一个？
就是有几个自由变量，然后最后的结果可以表示成自由变量和一个
对对对
矩阵和一个自由变量。
对对对，
那然后呢，是不是可以看成
向量不是矩阵。
这是对，是这样的，然后是不是可以看成以 x1 x2是它的系数，然后这两个是它的向量，
是啊，本来就这样。
然后呢，是不是就可以在几何里空间里画出来？
可以啊，可以
那它有什么意义？
啊，有什么意义吗？有啊有啊有啊，这个意义就是哦，你是说 null space 的意义啊？
嗯
可以，OK，我知道，可能知道你在说什么。你看回去我刚才一开始那个图像呢，OK，我觉得这个蛮好的，我等一下会在班上讲一下，我觉得这个挺在哪里啊？在哪里呢？
那个证明好不直观。
哪一个证明？
还有这种欧因特怎么证啊？它的定理啊，它只有一个定义是吧？
提问？什么意思？听不懂什么叫定义？
就是
你看这个 null space 就是这个 null space 就是上面一部分跟下面一部分去，再给我想一下，再给我讲一下，给我讲一下，它的 null space 是中间那条线，null space
送去零的这个 null space。OK，我等下用这个 example。OK，来，那个公 to 是怎么整？这个有这么一个公 to，而且，这里每一个就是只能用每一个，就是不是 one to one，它有一个说只要看零吗？哦，对，没有，对，没有错，对，非常。
把你的皮条
上星期，今天
今天的
这个，
我刚刚想问啥，我仔细回忆一下。哎，
没有啊，
刚刚有一个说到的
嗯
JS 的那个，
哼
就是我忘记是哪一个。
，homogeneous，
对，
这里有 homogeneous，然后最后有一页把它冷却，
我是
哎，奇怪，写到哪去被我 delete 了，有好几页好像，奇怪，对呀，我有一个算 dimension 的，对吗？然后 homogeneous，这里，
就是你刚刚说，哎，我感觉不是我想问那个，就是刚刚说有，它一般就是如果它只有一个solution 的话，然后可以用 homogeneous 给它，就是其他的解，就是 solution 加上一个，
哦，就是3次的，
对，
然后
就是我想问是，这个 homogeneous 它有什么意义？那就加还有什么用？
加上去是说你可以找到所有那个 AXB 的解咯。
这不影响这个方式。
有什么关联？
就是
有
比如说
什么关联？
我本来有一个解，然后我有个 solution，然后发现这几个东西它是 one to one，然后因为它只有一个 true solution，那它可以用 homogeneous 去把它这一个解改成好几个解。
哦，不能哦，就是你如果那个 matrix 是 one to one，意思说你 homogeneous 的解就一个，那个一个就是 zero vector。如果你再把它加上去之前那个解的话，还是之前那个解，所以你没加什么特别的东西上去。如果它不 one to one，就有一个 free variable，然后你就会加一大堆 infinite many 解进去。
懂了。
OK，
等一下。Okay. Uh, okay. So one of you come to ask me, how about the geometric interpretation for null A? Okay. So null space of A is everything gets sent to 0. Okay. Let's consider this example again. Okay. Let's consider back the T2 example again. So because T2 is not one-to-one, okay, so in particular, the null space is not just zero space. Can you guess what is the null space of T2? What are the vector get sent to 0? What are the vectors get sent to 0 by T2? what are the vectors get sent to 0 in T2? What vectors get smashed to the 0 point, 0 vector? Yeah. Any vector on the E3, yes. So everything on E3 will be mapped to 0 in this example. Okay. So algebraically, how you see it, sorry. So algebraically, how you see it, so you have 1, 0, 0, 1, 0, 0 as your matrix. Everything on E1 will be looking like 0, 0. Maybe what do I use? I use E3 again. Okay. And then for this, you get 0, 0, 0, 0, 0, 3, 0, 0. Okay. Okay. Am I right? Only 2, 0, right? So 0, 0. Okay. So everything on E3 will get sent to 0 vector. So the null space in this case is the E3 axis. Okay. Do you think you want to ask anything using? Huh? Next time. Okay. Okay. Let's continue. Okay. Let's continue. Determinant. Okay. We skip determinant as area in this course, so we won't see how determinant play around with areas. But if you want to know, as I said, suggest just now, you can go and watch the 3 blue 1 brown. I think they talk about it, and then they make animation on the area, and you can see how it changes. So at least for me, mathematics got two part of fun. Okay, one fun is people tell you how to do and you know how to do it. Second fun is after you do it, you know what's going on. Okay, so so learning this determinant is like the first fun. So people tell you there's this gadget here. Okay, try and play around with it and see what is going on. Okay. And second fun, you can try and go and look for the 3 blue 1 brown. So what's determinant? So last time when we encounter the inverse of when we try to find the inverse of 2 by 2 matrix, let's go on again. Let me restart. Okay, when we in the middle of finding 2 by 2 matrix, we found that there's something AD minus BC. We don't want it to be we want it to be non-zero such that the inverse exists, and then we call it a determinant. So determinant of 2 by 2 matrix is AD minus BC. Okay, so the product of the diagonal minus the difference of the product of diagonals. Okay, so second example is to find this determinant here. So let's quickly go through. So what's the determinant of this matrix here? Can someone quickly say a number? 0. Okay. So that means this is not invertible because the determinant is 0. Have we discussed whether determinant non-zero? I think we discussed, right? If the determinant is non-zero, then A is invertible. Okay. Okay, good. So this one is not invertible. And then next, next we want to form. So how about finding larger square matrices. So what's the formula finding it? This is what this chapter about. So how to find larger, for example, 3 by 3 matrix, 4 by 4 matrix, 5 by 5 matrix, how to find the determinant. And then any condition, yeah. So how to find the determinant of higher dimensional, higher size matrices. Okay, so first thing we will form is Aij. So Aij meaning you take away I row and j column. Okay, so maybe let's get some example. Let's see some example. For example, my A is 1, 3, and 0, 1, 3, 0, and then 2, 7, 0. Okay, let's say I want to form A11. Okay, meaning I take the first row away and then take the first column away, and then A11 will be the minor 1070. Okay. Similarly, let's say if I want to take away A21, okay, so that means what I do is I take away the A12, the row 2 and column 1. So what do I get? The minor I get is 2, 3, and 7, 0. Okay, so this is the notation of Aij. This is the notation of Aij, deleting row I and column j. So far, okay? Okay, so we will see how to use this to build the determinant. Okay, next. So next, so the theorem for the definition for the determinant of n by n matrix for n greater than or equal to 2 is given by this formula here. Okay. So the determinant is A11, okay, A11 multiply the determinant of the A11 minor, okay, where A12 and then multiply by the determinant of the A12 minor, and then you have this alternating sum here. Okay, anyone is first time seeing this theorem? Who is first time seeing this theorem here? Everyone seen this theorem before? No, definition. Can I see how many of you first time seeing this definition? First time. Hello, first time. Okay, most of you. Okay, never mind. Okay, so let us see what is this. Let us review what is this definition going on here using this example. Okay, so determinant of A is the sum of an alternating sum of Aij times the determinant of the minor. Okay, so how do you get this? Okay, so what I learned last time is how you determine how to put the sign on. So you can set out this plus minus plus minus plus minus plus minus plus. Okay, and then this plus and minus will correspond to the plus or minus we'll take for Aij here. Okay, so for example, A11 is a plus, so it's a plus here. A12 is a minus, so you got a minus here. Okay, and then it is what? It is this 1 to the power n plus 1 A1n. Okay, so that means you add the number of column to 1, and then we'll determine what's the sign of this coefficient here. Okay, let us try this example using this formula here. So in this case, we'll have determinant A11 times the determinant of A11 minus A12 determinant of A12 plus so let me see. So 1, 3, what happened? You have 1 minus to the power 3 plus 1, A13 determinant of. Okay, so do we stop here? Because there's only, this is 3 by 3 matrix, right? So you got 1, 2, 1, 1, 1, 1, 2, and 1, 3. Okay. 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 So what is A11 in this case? It is A11 in this case. 1. Okay. What's the determinant of A capital A11? What's the matrix of A11? A11 is minus 2, minus 1, 7, minus 2. And then take away A12. A12 is 5. Okay. And then multiply determinant of A12 is 3 minus 1, 4 minus 2. And then plus, what is A13? Is 0. 0, how to get this minor here? So you get 3 minus 2, 4, 7. So far okay or not? Okay. Okay. So next. So 2 by 2 matrix, you know how to compute, right? So it's 4 plus 7 minus 5 times minus 6 plus 4. Okay, so the determinant is 7, 11 minus, what's this? Minus 2 plus 10 equals to 21. So you just pick the first row to compute this determinant here. So far okay. Okay. If you ask why is this true, I think we won't cover this in this lecture. So maybe we just follow what is going on. Okay. After we get this, next part is a cofactor. Okay. So what cofactor doing is we want to consider this part here with this part. Okay, we combine the -1 with the determinant part, and then we call it a cofactor. Maybe let's call this a minor. After taking away row I and column J, we call it minor. Okay. We combine the -1 component with the determinant, we call it a cofactor. So let A be an n by n matrix. The cofactor Cij is defined with the -1 to the power ij determinant Aij. Okay, so this sign is determined by the sum of number of row and number of column multiplied with determinant of the minor Aij. Okay, so this will match up what I draw just now. Okay, so given a square matrix, right? So there's an immediate way to see what's the sign is. Because if you consider the 1, 1 here, 1 plus 1 is 2. So -1 to the power 2 is positive. Here is 1 plus 2, which is 3, which is odd. So odd is negative. Even is positive. Okay, and then so on. So you will form the grid of plus minus here. Okay, so you can determine this sign here immediately from this grid, plus minus grid. Okay, and then determinant of Aij, you will need to form the minor and then compute the determinant. Okay. So the next part is actually the next part says that you not only just expand the first row to compute the determinant. In fact, you can do it on any row or columns. Okay, you can do it on any columns. Okay, for example, what? Okay, for example, in 2 by 2 case, you can do it across this column here. Okay, first row, and then what you get is this formula here, and then which is the same AD minus BC. Okay, any how you expand it is the same as AD minus BC. So in this case, it's A11 times A22 minus A12 times A21. Do you want to verify this in class, or you believe this? I give you choice. Do you believe this or not? Or do you want to do it, check it together? Check it together? Okay. Okay, let's check it together. So let's see what's going on. So what's the A equals 1, A12, A21, A22. Okay. So the grid of plus minus is plus minus minus plus. Okay. So quick calculation for this. So the first thing we learn is we expand across the first row, right? So what we do is, what's the sign of A11? Is plus A11 times the minor you get after taking away the first row and the first column. Okay, so what you get is determinant of A22. Okay, and then minus A12 times the determinant of A. It is just A11 times A22 minus A12 times A21. Okay, so this matches up with the determinant of 2 by 2 cases. How about if we change row or column? Okay, we pick one of them and try. So which row we want to try? This one is the first row. Okay, so do you want to try second column? Let's try we compute determinant using second column. Okay, so second column meaning determinant A equals to, so following the formula we have minus A, A what? A12. Okay, if we get this coefficient out, then we take away row 1 and column 2, so we get the minor A21. So determinant of A21. Next one is plus A22 times determinant of, so we remove the second row and the second column, we get determinant of A11. Okay, so what we get is minus A12 times A21 plus A22 A12. So you can see that the two terms swap, but still giving you the same determinant function. Okay. Any can see over. So it's the same A22 times A11 minus A12 times A21. Okay. So you can expand across any row or any column. You will get the same determinant. Won't prove this, just that you need to know how to use it. Okay. Any question on how to use it? Any question on how to use this formula here? Or anyone not know how to read the formula? No response. Hello. A um okay. So far okay. So far okay. 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 I see some noting here. So in this case, try verify this page here. Okay. See that no matter which row or which column you expand using the formula, you will get the same product. Try verify this yourself. Okay. Okay, so compute the determinant of the matrix. What's the time? 926. Let's see how many things I need to go through first. Okay, maybe just try at home. Because I want to get to 3.2. Okay. Next theorem is if A is a triangular matrix, then the determinant A is the product of the entries in the main diagonal. Okay, this one is important. Let me show you an example here. Let me show you examples. For example, you have a diagonal matrix here. 4, 5, 6, 7, 0, 0, 0. Okay, so the claim is the determinant of this. Let me put a claim here. The determinant of this matrix here is just the product of diagonal 2 times 2 times 2, 3 times 2. Okay, so why is this true from the theorem? Maybe it's not obvious. So let's see what we do. Okay, so if we want to do cofactor expansion, which row you want to pick? Since every row and every column is the same, which row you want to pick? Huh? Last? You mean like this? Okay. Okay, good. So before that, let us put the grid on first so that we know what sign to put on every cofactor expansion. So we always start with a plus because it's even. So plus, minus, and then alternate. After that, minus, plus, and then plus, minus, plus, minus, plus. So these are the coefficient you have. So one of you, Seng, right? Yeah. So Seng suggests that we start from the fourth row. Let's start from fourth row. Okay. So let's see why it is good to start from fourth row. So fourth row, what do you have? So you have a determinant of the matrix. Is equal to, first you get minus 0 times the minor. So you get this 0. So you remove this row and column. So the minor is 0, 0, 5, 2, 1, 6, 0, 7, 3, 7. Okay. By the way, this is also notation for determinant. So let me introduce this easy shorthand notation. So we will write the modulus as a determinant as well. Because usually modulus will mean length. Okay, and then you will see that the first 3 terms are actually multiplied by 0. So multiply it by 0, we are happy because we don't need to calculate. It's just 0. Okay, so you can see that all these vanish by the 0. Only the last term survive. So you get plus 2 times the minor you get after removing the fourth row and the fourth column. So you get 2, 0, 0, 0, 2, 1, 0, 0, 3. Okay, so only the last term survive 2 times the determinant of 2, 0, 0, 2, 2, 1, 0, 0, 3. Okay, so it's not 2 by 2 matrix yet. Okay, so we can apply the definition recursively. So which row or column you want to pick next? Which row or column you want to pick next? Huh? To compute this 3 by 3 matrix, the determinant of 3 by 3 matrix, which row or column you want to pick next? Huh? Third row. Huh? Third, right? Okay. So you pick third. Fourth, huh? First row. Okay, you pick first row. Okay, good. Also can. First row also can. First row, let me write in another form first. So put the first row. Okay, first row you get 2 times 2 times 2 and then times the minor you get after removing the first row and first column. Okay, and then what the rest from the first row? You get 0. You get 2 times 0 times what's the minor? What's the minor after you're removing the first row and second column? What's the minor? What's the minor? What's the minor after you taking first row and second column? 0, 0, 0, 1, 0, 3. Okay, 0, 0, 1, 3. And then the sign is wrong, right? It should be a minus here, right? Because if you form the grid, you will have plus, minus, plus, minus, plus, minus, and then plus, minus. Okay, and then plus 2 times 0 times another minus 2. Okay, so in fact, you can see that first row also okay because there's less computation you do. So there's only one guy survive here. So it is D. The guy survive. Okay. So until now, so you left with a 2 by 2 matrix. So after you left with 2 by 2 matrix, you should be happy because you know how to compute the determinant of 2 by 2 matrix. So what do you get? You get 2 times 2 times 2 times 3 plus 1 times 0. Okay. So what's surviving here is 2 times 3. 3. Okay. So the diagonal product of diagonal survive again. But the other diagonal is 0. Okay. So in the end, it turns out to be 2 times 2 times 2 times 3, which is what we started. Okay. The order changed because you pick a different order to find the determinant. Okay. So if you pick the order like this, then you should have the same order of products. But the order changed here because you pick different row. Okay, so far okay? So far okay? So far so good? Okay. 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 So this one is very useful. So whenever you got a lower diagonal matrix or upper diagonal matrix, meaning 0 below the diagonal or 0 above the diagonal, then you can straight away take the product of diagonal to get the determinant. Okay, so this is very useful. You don't need to go over all this process again. You just take the product. Okay, so diagonal, upper triangular or lower triangular. Okay, next. Okay, next. Property of a determinant. Okay, so we know we can multiply elementary matrix to matrix, right? So, did we learn the determinant? Let's see. Actually, we haven't learned yet. Okay, never mind. Okay, we'll learn it after. So, determinant of EA. So after you do row reduction, right, to a matrix. Okay. So how does this determinant change? So the claim here is, if you do row reduction on A, and then you compute the determinant, is the same as you compute the determinant of A first, and then you multiply with determinant of E. Okay. Okay, so this is the claim. So, determinant E divide into 3 cases. So because you have 3 types of elementary row operations, one is row replacement, one is interchange, and then one is scale by R. Okay, let's remind us example. What kind of what are these 3 elementary row elementary matrix look like? So for row replacement, we will have something like 1 1 1 0 4 0 0 0 0. Okay, and then if it is interchange, E is the interchange, then we'll have something like swap between rows, and then 3 is a scale by R. So something like R1 1 0 0. Okay, this is what we did last week. Okay. So from here, row replacement. Is it obvious that the determinant of this matrix is 1? From what we learned just now? So if the matrix is triangular matrix, so here is the triangular matrix, right? So the determinant is just product of the diagonal. So it's just 1 times 1 times 1. So you get 1. So the determinant doesn't change. 2, okay, let's look at 2 later. Maybe look at 3 first. 3 scale by R. So this is also a triangular matrix. Okay, in particular, this is a diagonal matrix. So what you get is determinant is R times 1 times 1, which is R. Okay, so we have checked this 2. How about this one? Is this obvious? Why is it minus 1? Maybe not so obvious. Not so obvious, but if you try the core factor definition of determinant, then B is minus 1. It's minus 1. Okay. Do you want me to show the computation or no? Okay, you're happy? Okay. Yeah. Okay, next. Okay. So from what we have learned just now, we can see that if we have a square matrix, if 2 rows are exchanged, okay, then you will have an effect of multiply by minus 1 on the determinant of A. Okay. If the row is scaled by K, then the determinant is also scaled by k. If you have a replacement to produce b, then the determinant stay the same. Okay, this is what we discussed just now. Just like that. So let's try and use this technique and compute determinant of A. So let's try the technique of computing determinant of A. So far, how many ways we have gone through? So first is from the definition. So first we come from the definition. So call factor definition. Okay. So if we come from cofactor definition, what we can do is we choose to expand along one row or one column first. Okay. So for example, in this case, we can follow what column? What is the least work to do? Maybe we can pick the last column. So let's expand from last column. So start last row. Start from last row, sorry. Okay. So the grid of this matrix, the coefficient is plus, minus, plus, minus, plus, minus, and then plus, minus, plus. So we start from last row. So last row is -1. So what's the minor? So if you delete the first column and the last row, you get -4, 2, and -9. And then -7. Okay, -7. The minor is 1, 2, -2, -9. Okay, and then the last one is 0. So I purposely picked this row because I don't need to compute this minor here. So it's 0. So next is 2 by 2 matrix. So you are happy. So you can compute 9, 4, 36, -16, 8, 7, -9, plus 4. Okay, so what you get is -1 times 20, -7 times -5. So what you get is -20 plus 35. What you get is 15. Okay. Okay, it seems a lot of work done here. Okay, it seems. Let's see, we can use the elementary method to compute this. Okay, elementary matrix, meaning we can row reduce first and then we compute. Okay, let's see what's the easiest step to do. The step. What's the easiest step to do? Okay, let's do this. So determinant, I think not enough space. Let me copy everything over. Should I copy everything over? Let me copy everything over and okay. So let's start the new one. A equals to 1 minus 4, and then 2, 8 minus 9, plus 1, 7, 0. Okay, let's try introduce the row reduction to computing determinant A. Since we know the relation between elementary matrix and the original matrix. Okay, so first thing I'll do is determinant of A is the same as the determinant of, if I take row 2 plus 2 row 1 and then row 2, row 3 plus row 2, 1. Okay, so what I get is 1, 4 minus 4 is 2, and I get 0, and I get 0, and I get -5, and I get 0, 3, 2. Okay, why are they the same? By row replacement. So row replacement just now, doesn't change the determinant, right? So the determinant is the same as this one. So this one, okay, you can see that it's almost triangle already. Okay, how to make this triangle? These two swap. But when you swap, how do you change the determinant? Row interchange will introduce a -1. So this is equal to the minus of the determinant of 1 minus 4, 2, 0, 3, 2, 0, 0, minus 5. So this one is the by interchange. Interchange, what's the interchange? Row 2 with row 3. Okay, so from here, okay, here is easy. So here, because it's a triangular matrix, so this is a triangle. Where is the triangle? Triangle here. Okay, triangular, upper triangular in particular. So we get 1 times 3 times 5. So in the end, you get 15. So before you also get 15. So in the end, you also get 15. It's the same. Okay. So maybe in 3 by 3 cases, maybe the calculation set almost the same length. But when you go into larger and larger matrix, the cofactor will have longer step. Whereas for this, you can just reduce enough triangle, then you can get the determinant out. Okay. I suggest you to try this example using 2 methods. Okay, homework. Homework is go through maybe so go through the 2 method. Go through 2 methods to find determinant. Okay. Okay. Okay, next. Oh, actually, we haven't gone through here. So actually, it's this one. So a square matrix is invertible if only if the determinant of A is non-zero. Okay, so last time what we have learned. Okay, this theorem should follow from last time what we learned. So a square matrix is invertible if and only if it is row equivalent to the what matrix? Row equivalent to what matrix? Remember, a square matrix is invertible if it is row equivalent to the what? What kind of matrix? Yesterday. A square matrix is invertible if it is row equivalent to what? I. Oh, so the identity matrix. Okay. So recall what we did last time is we have an A, and then we multiply a sequence of elementary matrix, okay, such that it is equal to the identity matrix. Okay. So in this case, you can see that this one I throw away first. So in this case, so let's compute the determinant of both sides. Sorry, I missed something. So determinant of okay. So just now we learned that determinant of elementary matrix with any matrix, we can split out the determinant. So the determinant is multiplicative. on the elementary matrix. Okay, so we can split it up one by one. It's multiplicative on the elementary matrix. Okay, so we can split them up. Determinant of A equals to, what's the determinant of the identity? 1, because identity is a triangular matrix, so you just take the product. So 1 times 1 all the way. So in this case, can you deduce what's the determinant of A? What are the possibility of determinant of EI? Either it is 1, either it is some scale R, either it is -1. So it is just minus times some number, just some number, non-zero number. Okay, so let's let the product of E n up to EI to be C, where C is non-zero. Then determinant of A is 1 over C, which is also non-zero. Okay, so the determinant of A is non-zero. So from here, we can see that we can check whether A is invertible or not by computing the determinant first. Okay. Yeah. Okay. So far, okay. So want to compute again. Do we want to compare? Skip. This one just left with homework. It's the same exercise we did just now, finding the determinant. So the next part is if you transpose your matrix, okay, the two determinant is the same. Okay, why? Determinant can be computed using every row or column. So if you transpose it, does the row or column change? The row change to column, yes, but it's still the same sequence of number. Can you imagine? Can you imagine or not? Okay. So if you got a row or column, after you transpose, it's the same sequence of number. So you get the same number. Okay. Make sense? Okay. Okay, good. So this part, okay, determinant of AT is equal to determinant of A. So this means that if A is invertible, you transpose it, it is still invertible. Right? Because if it is non-zero, then it's still non-zero after you transpose it. For determinant, because they are the same. And then the next part is harder. The determinant of AB is equal to determinant of A times determinant of B. So this is what? This is multiplicative property. Okay. This is the same similar square we draw last time. So if you got an AB, and then you can multiply them together, and then you apply determinant, you get determinant of AB. Or you can apply determinant to both of them first, and then you multiply them. So the ideal case is we want them to be the same. In this case, they are. In this case, they are. Do you want to see a proof or it's fine? Huh? On the proof? Okay. Okay, very good. Very good. If you want to, yeah, very good, very good. Good, good, good. Yeah, very good. and see a proof. Okay, two cases. We break into two cases. Okay, one cases is A is invertible. It's not invertible. And then second cases is A is invertible. A is invertible. Okay, let's see I will fail or success. Let's try. Get rid of this. Yeah, maybe let's just start with new pages. Yes. So yeah, we will end this lecture with this proof here. Depending on how long it takes, then we will start quizzes afterwards. Okay, so claim is determinant of AB is equal to determinant of A times determinant of B. So two cases proof is kind of good. So one cases, two cases to consider. Cases to consider. So one cases is A is not invertible. So just now we know that if it is not invertible, that means determinant of A is what? 0. Okay, because if it is invertible, if and only if it is 0. So if and only if it is not, then the other is not. So if A is not invertible, then AB is also not invertible. So determinant of AB is 0 again. Okay, so I don't need to know what is determinant of B. 0 equals to 0 times anything. Okay, so this equation holds. So this equation, determinant of AB equals to determinant B. Okay, next, suppose A is invertible. Okay, so what do we do if A is invertible? A is invertible, what do we do? If A is invertible, what do we do? What can we do? If A is invertible, what can we do? Okay, so what can we do? Ah, what can we do if A is invertible? Idea. B is equal to identity times B, which is equal to A inverse times A B. Okay. Right. So what can we do? What can we do? I think a bit. What can we do? I think a bit. What can we do? Can you use something from the row reduction? Can you use something from the row reduction? Idea? Can use something from the row reduction or not? No idea. Okay, let me try again. Okay, so remember how we find the inverse of A from last time? Last time, how we find the A inverse? Still remember? Still remember? So we said that A can be row reduced to identity. Yeah. So that means you have a sequence of people of elementary matrix that you get to identity. Okay. So from here, what do you get? A is actually the inverse of sequence of elementary matrix. And then the inverse of elementary sequence of matrix is still elementary matrix. Okay, so maybe I replace with E prime, U prime, E1 prime. Okay. So from here, should be good now. So what is determinant of AB? So determinant of AB is equal to determinant of En prime dot E2 prime dot E1 and B. But we know that we can split off all the elementary matrix because determinant is multiplicative on elementary matrix. So we can split all of them off so that we get E prime to E1 prime times determinant of B. Okay, but En prime times up to E1 prime is just a determinant. So what do we use here? We actually use that determinant is multiplicative element. Okay. So what we use is this theorem here. So we can split off E. So determinant of A is multiplicative on elementary matrix. Okay. We didn't prove this. Right? We didn't prove this, but we use it in this proof here. Okay. Any question? Any question? Any question or not? Question? Any question? If not, let me see how many minutes we have. 30, 40, 30. If we wait until 30, 45, 45, 30. Okay. Let's break. Let's take a 10 minutes long break. 10, 15, we'll come back for test.
4等于0的话，它是 onto 哦。
不会，它只是 consistent 吧，它不 onto，因为 onto 的话要 for 每一个
哦，就是这里全部都要一个，
都要 consistent。
所以这个算 consistent 吧，这个不 consistent。
就是 v4不等于0的时候，它就不 consistent。但是你要 onto 的话，你要对 for 所有的 b。
哦，所以如果 v4等于0，它也不是 onto。
onto 呀，onto 是每一个 b 你都要 consistent。
theorem of order non-trivial and one-to-one.
Yeah, you can use this.
Think it's
Useful.
easy.
Very easy. Yeah, you can. Okay. What's your name?
Sounds
Okay. Yeah, you can. Okay.
所以我算的时候就很像，我就算到这样子，然后下面0就可以了，就直接有数字的就不用紧了。
怎么都对。
然后 one-to-one 跟 on-to，
啊，
然后我算到这边1，然后1的下面0，就上面的号码我就不用管了。
那你讲，你要讲，就是你讲解释。
就像这样子，就是写every，你这样
every row have a，
但是它这个不是 one-to-one，也不是 on-to-one。
这个不是 one to one，也不是 one to，对，这个不是 one to one，也不是对。
对，我就可以算到这样子就停了。然后我就写 zero and columns are not does not have pivot at every row and column。对，我算到这边就会直接就不用把这个2消掉。
这个 case 2消不掉。
假设
你是讲如果这个上面有东西的话，不用消掉啊？可以。 啊，可以，
就只要
因为我们 K 的是 pivot column 嘛，我们不给它的 range row 上。
像如果 independence 跟 dependence 也是一样，然后嘛是可以，就不用把它设成
上面的号小声。
就如果他叫我证明，就
啊
证明 independence、dependence、trivial、non-trivial，还有那个
这个用我刚才讲下面是零这样之类的，
就只要下面全部是零就可以。就我上面好像这种，然后如果这里5、4那种算了，就是好的，还是我一定要做到完，就全部零跟全部一。
来，我要看看你的题目长怎样的先，
嗯，因为
有模糊，有模糊。
看
Okay, make sure you sign the attendance sheet. Need to know who are absent. And then 1 more minute. Maybe someone's still in the toilet. So later we will split the class into 4 groups like this, 4 group. Okay. I want the first person in the row. Anyone volunteer? First person, the first. And then count how many person in your group, and then come and collect. Okay, as usual. So I will provide, look, but when you get the sheet later, don't start first. Sheet, you can read first, and then we'll start together. So the sheet like this. So I hope it's enough space for you to write. There's 4 questions here, 25 marks in total. Percentage is 11. Contribute to final. And if you do not enough paper, you can ask from me later. I hope it's enough. Should be not long question. What's that? Oh, pass to the right. Pass to the right. Okay, it's 10:15 now, so every group can get 1 person here, and then get this paper. Once you get the paper, you can read first, but don't start yet. We will start together. The question shouldn't be long unless you did some mistake, so you can get some paper from me. Don't start yet, you can read first. Make sure you write down your name and ID, otherwise I cannot track you down. Start here, you can read first. Enough paper or not? 18 or 18. Everyone got it? Yeah. Everyone got it? Got extra or not? Extra? So let's start 10:18 and then we'll stop at 10:48. about 10 minutes left. Few more minutes. So check your answer, clean up your solution, and then check your name, ID. Once you're done, you can pass to the front. Just pass to the front. And the person who collect, please check the number is correct based on the number. So 63 of you attended, so all of you come. Sign it, please sign it before you leave later. So some of you haven't signed it. Sign, yeah, haven't signed your attendance.折一下，它哪里有的？折一点，折一下。 I think there's one more from the last. One more. Okay. There's one last. Who? If I don't receive it. Okay, thanks everyone. So we'll see you again 9 o'clock. If I manage to finish marking tonight, then you will see the result tomorrow. Okay. Thank you. See you tomorrow at 9.
问啊，说
你的高数的问题，
几时来？
我现在来。
现在我们去吃饭了，你要跟我们去吃饭？
我问个问题啊。
好啊，我呢？
拿问题吧。
是不是小九州啊？那里很好吃。
小九州哦。
只是写不出来，我浑身难受。
好，等一下我听一下。